Ever wonder how your data zips across the vast expanse of the internet, reaching its destination seemingly in the blink of an eye? Well, it's all thanks to the intricate dance of IP addressing and routing protocols. Picture this: each device on a network is assigned a unique address, much like houses on a street, allowing data packets to find their way to the right recipient. And just like GPS guiding you through traffic, routing algorithms determine the best path for your data to travel, navigating the digital highways of the world. So, let's dive into the fascinating realm of IP and routing, unraveling the invisible threads that connect us all. Remember, understanding these fundamentals is key to unlocking the secrets of network connectivity and reliability. Welcome to our journey through networking essentials. Today, we dive into the world of IP addressing, where IPv4 meets IPv6 in a dynamic dance of connectivity. Subnetting awaits, revealing the art of segmenting networks for efficiency. Then, we unravel the mystery of routing mechanisms, unveiling the intelligence behind packet forwarding. NAT translation emerges as a crucial player, conserving precious IP addresses. And finally, we embark on a traceroute analysis adventure, mapping the path of your data across the vast internet landscape. Get ready to unravel the secrets of networking intricacies and empower your understanding. In 1981, IPv4 emerged as the cornerstone of internet communication, utilizing 32-bit addresses divided into 4 octets. Ranging from 0 to 255, these octets form familiar addresses like 192.168.1.1 or 10.0.0.5, granting around 4.3 billion unique identifiers. Initially seen as limitless, this number now falls short in our interconnected era. Remember the historical address classes: A for large networks, B for medium, and C for small, though this system is mostly outdated. Recognizing these ranges can aid in troubleshooting older network setups. In our quest for connectivity, IPv4's constraints have become apparent. Not all IP addresses are created equal. Special IPv4 address ranges serve distinct purposes in network design. Private networks, like 10.0.0.0/8, offer vast addresses for large organizations. Meanwhile, the 172.16.0.0/12 range is ideal for medium networks. For homes and small offices, 192.168.0.0/16 provides ample addresses. Now, the loopback address, 127.0.0.1, uniquely refers to this computer, crucial for software testing. In cases of DHCP failure, the 169.254.0.0/16 link local addresses step in, enabling limited local communication. Remember, understanding these reserved ranges is key for effective network management and troubleshooting. In a world where the demand for internet addresses is ever-growing, IPv6 emerges as the solution to IPv4's limitations. With its 128-bit structure, IPv6 boasts an incredible 340 undecillion addresses. That's enough to assign thousands to every grain of sand on Earth. Formatted in 8 groups of 4 hexadecimal digits separated by colons, such as 2001 DB8:85A3 8A2E 370:7334, IPv6 offers a vast pool of addresses without the need for NAT in most cases. Its benefits extend to built-in security features like IPsec, a simplified header structure for faster routing, and enhanced support for mobile devices. The future of internet addressing is here, with IPv6 paving the way for a more connected and secure digital landscape. Ever wondered about the key differences between IPv4 and IPv6? Let's dive in. In terms of address length, IPv4 uses 32 bits, providing around 4.3 billion addresses, while IPv6 boasts 128 bits, equating to a staggering 340 undecillion addresses. Moving on to address notation, IPv4 sticks to decimal like 192.168.1.1, whereas IPv6 opts for hexadecimal such as 2001 DB8:1. Configuration-wise, IPv4 typically requires manual setup or DHCP, whereas IPv6 supports auto-configuration through SLAAC. When it comes to security, IPv4 leaves it optional, while IPv6 integrates IPsec right into the protocol. NAT dependency varies too. IPv4 heavily relies on NAT due to an address shortage, while IPv6 is designed to eliminate the need for it. In conclusion, IPv4 and IPv6 present distinct characteristics that cater to different technological needs, with IPv6 offering vast improvements in scalability and security. Subnetting is a key technique in network management, essential for optimizing performance and enhancing security. By dividing a larger network into smaller subnetworks, organizations can efficiently allocate address space, reduce broadcast traffic, enhance security by isolating sensitive systems, and organize devices logically. Imagine a university with separate subnets for student wireless devices, administrative systems, research laboratories, and public guest access. Subnetting provides a structured approach to network organization, improving efficiency, performance, security, and overall management. Ever wonder how networks determine which part of an IP address is for the network and which is for the host? Enter subnet masks and CIDR notation. Subnet masks, like 255.255.255.0, use binary to designate network and host portions. CIDR, such as 192.168.1.0/24, simplifies this with a concise count of network bits. For example, /24 equals 24 network bits and 8 host bits, offering 256 addresses. Need to calculate hosts? Use the formula 2 32 prefix, 2. With /24, that's 254 usable hosts after subtracting the network and broadcast addresses. Streamlined, efficient, and essential for modern networking. Ever wondered about the magic behind network capacity estimation? Enter common subnet sizes. CIDR prefixes like /8, /16, and /24 unveil a world of efficiency. Picture the vast 16,777,214 hosts in private networks under /8, or the 254 in a small business subnet with /24. Need just 2 hosts for a router link? /30 is your go-to. Remember, each prefix tells a unique network story. Master these sizes, and network planning becomes a breeze. Size matters in the world of CIDR. Imagine dividing a network like 192.168.100.0/24 into 4 subnets tailored for sales, engineering, marketing, and support. To achieve this, we first determine the bits needed, here, 2 bits for 4 subnets. By adjusting the prefix to /26, each subnet offers 62 usable hosts. The subnet ranges increase by 64, resulting in distinct allocations for sales, engineering, marketing, and support. Remember, the first and last addresses in each subnet are reserved for network and broadcast addresses, not for hosts. In essence, subnetting efficiently carves out specific spaces within a network for various departments' needs. Ever wonder how data finds its way across vast networks? Enter routing. It's the art of navigating packets from point A to point B. Picture routers as digital traffic directors, using intricate maps called routing tables to guide data on its journey. From the source device to the local router, then through a series of internet routers, each hop brings the packet closer to its destination. Finally, after traversing multiple networks, the packet reaches its endpoint. Routing is the unsung hero behind seamless connectivity. Just as roads guide us to our destinations, routers pave the way for data to travel swiftly and securely. Ever wondered how routers know where to send your data? Enter routing tables, the brains behind the scenes. These tables are like maps, guiding packets to their destinations. Each entry includes vital info, the destination network, subnet mask, next hop, interface, and metric. Think of it as a routing GPS. And don't forget the default route, a safety net for unknown paths. When faced with options, the router chooses wisely, following the most specific route available. Routing tables, the unsung heroes of network navigation. Ever wondered about the fundamental difference between static and dynamic routing in networking? Static routing involves manual configuration by network administrators, offering predictability and security without the protocol overhead. However, this method can be time-consuming for larger networks and lacks automatic adaptability to failures. Conversely, dynamic routing automatically shares and updates routing information through protocols, adapting to changes and scaling effectively in large networks. While more complex to set up initially, dynamic routing excels in self-healing capabilities when links fail. So, for small networks or specific critical paths, static routing may be the way to go, while large, complex networks requiring resilience would benefit most from dynamic routing. In essence, the choice between static and dynamic routing boils down to the network size and the desired level of automation and adaptability. Ever wonder how routers know where to send data in a network? Routing protocols hold the key, like the diverse trio we'll explore. RIP, with its simple hop count metric, suits cozy networks but lacks scalability. In contrast, OSPF shines with its bandwidth-based cost metric, perfect for expansive, hierarchical setups. And then there's BGP, the Internet's linchpin, steering traffic across autonomous systems with finesse. Each protocol plays a vital role in shaping our digital highways. Choose wisely to pave the way for efficient, smooth data flow in your network. Ever wonder how multiple devices can share a single public IP address? Enter Network Address Translation, or NAT. Originally a solution to IPv4 address depletion, NAT is now a cornerstone of modern networks, offering both efficiency and security. Here's how it works: a device on a private network sends data to the Internet. The NAT router then substitutes the source IP with its own public IP and keeps track of the connection details. When the response arrives, the router uses this information to direct it back to the correct device. There are different types of NAT, such as static NAT for one-to-one mapping, dynamic NAT with a pool of addresses, and PAT for many-to-one connections. While NAT adds a layer of security by concealing internal network details, it should never replace a dedicated firewall. In essence, NAT streamlines connectivity while safeguarding network integrity. Ever wonder how Network Address Translation, or NAT, works its magic? Let's dive in. NAT serves up a buffet of benefits and limitations. It's like a master chef at a crowded restaurant, making sure every device gets a taste of the Internet using one public IP address. This conservation effort is crucial as IPv4 addresses become rarer than a blue moon. But NAT isn't just about sharing. It's a security guard too, shielding your internal network from prying eyes. Yet, like any complex dish, NAT has its drawbacks. Some applications may stumble, needing extra TLC for connectivity. And beware the performance toll: processing overhead and latency can sneak in during peak traffic. Hosting services? Prepare for a port forwarding puzzle. NAT, a multifaceted tool in the networking kitchen. Ever wondered how network administrators trace the path packets take through complex networks? Enter Traceroute. This powerful diagnostic tool unveils the journey packets embark on, hop by hop, shedding light on connectivity issues, latency measurements, and network structures. Leveraging the time-to-live field and IP packets, Traceroute cleverly maneuvers through routers, incrementing TTL values until it reaches its destination. Windows users type traceroute.google.com, while Mac and Linux users opt for traceroute.google.com. The output reveals hop numbers, round-trip times, and router details, with **** indicating a timeout. With Traceroute, network troubleshooting becomes a precise science, empowering administrators to navigate and optimize network performance seamlessly. Ever wonder how to decipher Traceroute results like a pro? Well, let's break it down. The sequence of hops reveals crucial information about the path to your destination. Look out for latency spikes, they could signal trouble ahead. Keep an eye out for outlier hops with unusually high latency, they might pinpoint problem areas. And remember, not all silence is alarming, some routers prefer to stay incognito. By tracking hostname clues, you can uncover the hidden geography of your data's journey. So, next time you run a traceroute, decode the data like a seasoned detective. Is your website failing to load or suffering from slow connection speeds? Traceroute is your troubleshooting ally. When packets hit roadblocks at specific hops, pinpoint router failures. High latency at early hops signals local network issues, while delays further along point to ISP troubles. For regional access woes, trace from various locations to unveil routing problems. Remember, clarity is key, act swiftly to resolve connectivity gremlins. As we wrap up Chapter 2, let's recap some key points. IP addressing. IPv4 uses 32-bit addresses, IPv6 uses 128-bit addresses, offering near-limitless possibilities. Subnetting. Divide networks efficiently using CIDR notation. Remember, /24 equals 254 hosts. Routing. Routers steer packets via tables, with dynamic protocols like RIP and OSPF adjusting automatically. NAT enables multiple devices to share a single public IP, crucial for IPv4 conservation. Traceroute helps diagnose issues by mapping packet paths and latency. Armed with this knowledge, tackle network challenges confidently and refine your architectural designs through hands-on practice. Remember, a well-designed network is a reliable network.